Please, Ryosuke, thanks.
Hello, I'm Ryosuke Akashi from National Institute for Quantum Science and Technology. Recently, I moved from University of Tokyo. So today, I'm talking about a very simple theoretical analysis on how the Eliashberg equation behaves in the okay. How the Eliashberg equation behaves in the uniform electron gas. So probably all the audience are familiar with this equation, Macmillan-Arendines. Thanks. Macmillan-Arendines formula. So this is, very useful for estimating the superconducting transition temperature based on a phonon-mediated superconducting theory. And usual usage of this is we estimate we calculate the omega ln factor representing the typical phonon frequency that couples the electron, and also the lambda representing the strength of the electron coupling from first principles. But on the other hand, the electron-electron Coulomb repulsion that suppresses the Coulomb interaction is usually treated as an empirical parameter, where, for example, we use the typical value like 0.10 or 0.13. But of course, with this method, we are missing some important quantitative or even qualitative effects of electron-electron Coulomb interaction. So with this, we cannot complete the ab initio calculation of transition temperature. So basically, this talk is about the ab initio treatment of electron-electron Coulomb interaction. And the Macmillan's equation is derived from Migdal-Eliashberg theory for phonon-mediated superconductors. So this theory starts from this Hamiltonian. Here, the electronic one-body term is represented by the Kohn-Sham Hamiltonian, and the phononic one-body part, and the electron-phonon interaction part, and the electron-electron Coulomb interaction part. And all the components are basically evaluated by the Kohn-Sham calculation for first principle calculation. So, and in this theory, we treat the interacting Green's function in a 2×2 Nambu-Golgov form. So in this expression, the diagonal term represents the normal Green's function, and the non-diagonal part represents the anomalous Green's function. That becomes non-zero only in superconducting regime. And the Dyson equation relates the interacting Green's function to the self-energy. And in this theory, we approximate the self-energy so that we only incorporate those two lowest order self-energy terms with respect to phonon propagator and the electron-electron screened Coulomb repulsion W. So in principle, with this approximation, we can treat the physics like a phonon-mediated attraction for pairing and the electronic mass renormalization and the pair suppressing Coulomb repulsion and the retardation effect coming from the timescale difference of phonon-mediated and the Coulomb interactions. So, but in practice, we treat the latter term as an empirical parameter, and we do not directly calculate this. But here there are already some attempts to, of course, calculate this part from first principles. So actually, differently from phonon-mediated self-energy, the Coulomb self-energy part, when we consider the calculation of Coulomb self-energy part, there's fundamental difficulty that there's no good expansion parameter for the higher order self-energy due to screened Coulomb interaction. So there's no justification why we can truncate the summation up to only the first order, but still it would be very informative if we can completely understand the lowest order approximation, how the lowest order approximation behaves. So for example, by considering the random phase approximation for the screening, for metallic screening. So that's the purpose of my study. Okay, so here I do some review on to what extent the electronic self-energy has been analyzed from first principles. So this is the Eliashberg equations are for the self-consistent equations for the components of self-energy that are decomposed by the Pauli matrices sigma 0, sigma 1, sigma 3. And Eliashberg equations are the self-consistent equations for those three components, z, chi, phi. And we start from this point. And usually the phononic contribution to chi part is legitimately ignored because of the argument by Schrieffer that is based on electron phonon, approximate electron phonon symmetry, electron hole symmetry, sorry. So, and about the electronic part, so the most elementary approximation would be the static screening approximation to the anomalous part. So you remember the sigma 1 part represents the non-diagonal part of self-energy, so related to the superconductivity. So at this point, usually the normal self-energy contributions to Z and chi are ignored. And we apply static or instantaneous approximation to the screen-Coulomb interaction entering the anomalous part. And interestingly, already at this point, we can do the accurate practical calculation of superconducting TC. So, after recasting the problem to superconducting DFT, the Hardy and Antonio and Camila in the audience has presented this kind of beautiful demonstration. And also, more recently, a direct solution of not the SCDFT, but the Eliashberg equation has also been demonstrated by Hardy and Ryotaro in the audience. So a next level approximation would be to include the omega dependence of W in the anomalous self-energy. And actually, in principle, with this treatment, we can consider the plasmon effect. So, and actually, several years ago, I demonstrated the plasmonic assistance or enhancement of superconductivity in cooperation with the phonons. So using the superconducting DFT. So in some trivial systems, the enhancement due to plasmonic effect is like small like this. But in some system like FCC lithium under pressure, the enhancement is significant. And afterwards, also the effect of plasmons to the normal self-energy part has also been partially explored. So this is a work also by Antonio and Hardy. So they consider the plasmonic dependence to Z term of the self-energy, and show that this self-energy effect reduces the superconducting transition temperature calculated from Eliashberg equation from green points to purple points for various typical phonon-mediated superconductors. So this result suggests that the plasmonic effect on normal state self-energy may somehow cancel the plasmonic enhancement. So with this result, one would be interested in the remaining term chi. But actually, there has been a reason why the chi in ab initio calculation was intact. So although I skipped the detail, the chi is very extremely difficult to computationally demanding to handle. So, so actually, it's still difficult to calculate this term from first principles. So with this, I decided to first examine the effect of screen-Coulomb interaction on chi in a very simple system so that I can complete the calculation. That is the uniform electron gas. Okay, so let me introduce my model. So the electronic system is a uniform gas. So the spectrum has a parabolic dispersion. And this is the bare Coulomb interaction. for electrons. And this is actually not the trivial uniform electron gas. I also consider a phonon effect as an Einstein model with tunable coupling and frequency parameters. So here, electron phone coupling only depends on, is controlled by the parameter of coupling strength lambda and the Einstein frequency omega e, and NF is the electronic density of states at the Fermi level. And with this Einstein model, the phononic propagator is also independent of the electronic wave numbers. And for electron-electron Coulomb interaction, I adopted random phase approximation, where the dialectic function is a form of a Lindhardt within random phase approximation. So, for analysis, I adopted some very simplified approach. So, although I consider the full electron-electron Coulomb interaction self-energy part, some parts are ignored, like trivial phononic contribution to chi. And here I adopt the approximation like first, I wanted to concentrate on the onset of superconductivity, so I ignore the anomalous self-energy when calculating the normal self-energies. And I also neglect the electron phonon renormalization effect in order to concentrate on the electron-electron renormalization. And finally, I execute just a one-shot calculation where I calculate Z and chi using the non-interacting values of Z and chi. And finally, we insert these Z and chi to the anomalous equation and solve this self-consistently. So this approximation corresponds to the G0 W0 approximation for in the GW community. So, okay. So now we are moving to the result. So first, I'm showing the inverse correction of the inverse effective mass. So this plot shows the dependence of the value on RS parameter, representing the inverse density of the electron gas, representing the typical distance between electrons. So and here yellow curve shows us the contribution due to Z term, and the blue curve represents the contribution of the chi term, and the total correction is the summation of those two, represented by purple or green lines, depending on subtle approximation. So anyway, important thing is that both the contribution due to Z and chi have sizable effect, but in total, these almost cancel. So actually this result, the cancellation of Z and chi have been well known in the GW community, but to my impression, maybe less known in superconducting community, I guess. Oh, sorry. Okay, so next we are moving to pairing strengths. So for this, I first linearize the equation for anomalous part, and the parameter is fixed to those settings that is actually realizable in, for example, compressed light element superconductors. So with this linearized approximation, I evaluated the largest eigenvalue of the linearized equation in order to estimate the pairing strengths. So this approach can be understood like this. So in high temperature limit, the eigenvalues are trivially 0. But as we come down to the low temperature, the eigenvalues will grow. And when one of the eigenvalues reach to unity, it means that there's a self-consistent solution of this linear equation. So by estimating the largest eigenvalue of this equation, we can evaluate the strengths of the pairing depending on the approximation. So now we are seeing the result. So here I plot again the RS dependence of the largest eigenvalue ratio, ratio between the value without z and chi and with z and chi in inverse manner. So values larger than unity means the suppression of the pairing strength. So here the blue points represent the result with only z term, and the purple point represents the result with both z and chi terms. And the green and yellow lines represent some analytical expression derived from some my analysis. So anyway, the important result is that in the pairing renormalization case, pairing strength case, z term and chi term cooperatively suppress the pairing. So let's summarize the result at this point. So here we have seen the mass renormalization and pairing renormalization behaves quite differently. And actually the formula of those can be well represented by those formulas. Here the factors, correction factors, delta z and delta chi are related to the Fermi surface values of z at the Fermi surface and the wave number derivative of chi at the Fermi surface. And importantly, in the uniform electron gas, both factors are of order of 0.1 and has substantial impact on both the mass and pairing. So, actually, the departure of two renormalizations are somehow non-trivial in the electron phonon world. So when we only concentrate on the electron phonon interaction, so probably many of you can remember the formulas for mass renormalization and the transition temperature like this. So here we see that these are dominated by the same factor 1 plus lambda here and here. And often this lambda is called mass enhancement factor. So the electron phonon case, this renormalization behaves in the same way. And one may think if transition temperature renormalization is due to mass enhancement. But now, after having the analysis with chi, we already know that the situation is different. So actually, the dependence of mass and pairing corrections behave like this. But in phononic case, we remember that the contribution to chi was physically negligible. And without this chi factor, we have the same factors. So actually, we are seeing that the mass and pairings are renormalized by same factor, even in the phonon case, but it is just a spurious correlation. There's no relation between those. So finally, I'm explaining those two renormalizations are coming from the different physics. So actually, the spectral renormalization effect matters. So for this, I recall the effect of z and the derivative of chi. So first, z reduces the spectral weight of Green's function by factor 1 over z. And at the same time, it reduces the bandwidth by 1 over z. On the other hand, the derivative of chi increases the bandwidth by the factor 1 plus del chi. And the mass renormalization is determined by the product of those factors, as I have mentioned earlier. And on the other hand, how about the pairing? For that, we remember that z, we normalize the anomalous Green's function by a different factor, 1 over z squared. And remember that the anomalous self-energy equation has a form of a state summation with respect to the product of anomalous Green's function and interaction. So from these formulas, we can evaluate how the summation is renormalized. So the spectral weight of anomalous Green's function is reduced by this factor. And at the same time, z induces the state increase by band narrowing. And finally, the del chi term induces a state decrease by band widening. And as the product, we get the factor here. So what induces the pairing renormalization is the total change of the electron number contributing to the pairing near the Fermi surface. So after understanding this, I did some thorough re-investigation of the previous works, and I finally found some similar equation. It has been already obtained by Rich and Sham long years ago. So in this paper, they analyzed the effective pseudopotential without phonons within RPA. And in their formula, this C over T term represents the renormalized Coulomb interaction due to retardation effect. Due to sort of retardation effect between plasmon and the static Coulomb. And in their notation, Z and D represent respectively the Z term effect and the K derivative of chi. So actually, this already captures the same physics as mine. So finally, what I did recently is that to clarify that this effect originates from the spectral renormalization, and it works. It's valid with even with the phononic degree of freedom, and give a correct interpretation how this occurs. So this is a summary of my talk. So I examined the Eliashberg equation in uniform electron gas with RPA and G0W0 approximation. And I show and understood the mass and pairing renormalizations are different, completely different. And also we have seen that if we want to evaluate the transition temperature accurately, we need to include both and chi at the same time. And otherwise transition temperature should be overestimated. And finally, let me also mention some side result in this paper. So here I derived the exact analytical expression of some singular term in RPSF energy. So although it's trivially known that this has a component of order of K log K near the Fermi level, to my knowledge, it would be the first time that that we see the exact expression. Okay, so thank you for your attention.